Gaussian beam optics, and what we did in this lab is we inserted a beam expander, a collimating lens, to create a beam expander, which is effectively a Keplerian telescope of two positive lenses, the microscope objective, and the collimating lens. And what we did is, by creating a beam expander with a larger collimated beam out, we were able to get a smaller spot size that was 10% of the beam waist at the focus than last week.
So here we're using a spatial filter so that we can have a clean Gaussian beam propagating through our system. As the beam goes through our objective lens, there's some noise that comes from high spatial frequencies of dirt and dust on the lens, and then the lens will take a Fourier transform, so we see those as the beam goes through the system. So here we see an airy disk pattern on this paper, and we want to cut out the outside rings but get as much of the energy through as possible. So we're using a 25 micron pinhole with our 16mm objective lens, as recommended by a Newport application note. And to align the spatial filter, it's kind of an iterative process of translating the objective a little bit and then readjusting the X and Y coordinates. So you can see we got rid of a couple of the rings already, and the beam is getting cleaner, and eventually we'll just have one strong blob, which is that center lobe of the Gaussian profile that we want to use for the rest of our system.
Okay, so here we placed a shear plate behind our collimated laser beam. So what we can see here is some interference fringes caused by a piece of glass inside the plate, inside the box, which has some wedge in it, and so we have a different optical path length from the reflection off the front surface and the rear surface of the glass, and that's what causes these fringes. So we can see here a sort of cubic shape on the fringes, which is indicative of spherical aberration in our lens. And so basically we've put the collimating lens the wrong way around. So if I turn it around, if I can, then we can look back at our fringes, and they're actually almost aligned already. And so I can just do a little bit of work lining them up. And now we can see straight line fringes. Oh no, actually it's probably not really aligned, is it? There we go. Yeah, it was. Okay. So now we can see straight line fringes on our shear plate, which are going along this 0 degree angle mark, and that's indicative that we have a collimated beam going outward. Pause. So here I've turned the lens around to correct that spherical aberration, and we can see that the fringes aren't lined up with the 0 mark on the shear plate, and the angle that they're off by is actually proportional to the radius of curvature, or the sine of the angle, inversely proportional. So right now I'm actually past focus, so if we move the lens we can see the angle changes until it's lined up, and that's indicative that we are actually collimated now. If I keep moving, then now we're inside focus and we have a diverging beam, and so it is angled the other way. So now we can go back to collimated. So we also tested using a smaller shear plate, and we can see that we get the same sort of behavior, although as I turn the micrometer to move the collimating lens, the angle doesn't change quite as much. In fact, we find that the range of motion here, where it's still about straight, is about 25 mils, whereas for the larger shear plate it was only about 10 mils. And so that can be explained by the shear distance on the larger shear plate being larger, and the sine of the angle is proportional to that shear distance.
Okay, so for this part of the lab we profiled the beam with a knife edge before and after the beam waist, where the rays were converging and diverging by the same method as last week with the knife edge and scanning across the beam with a photodetector.